So now it's 2 o'clock, and I would like to welcome everyone to this webinar, which is arranged by the Swedish Concrete Association and organized by the research committee of the Swedish Concrete Association. And today we will have a webinar where we will talk about new alternative binders and their implementation. And today we are lucky to have invited lecturers. We have Ruben Snellings that will start the talk from KU Leuven, and Clarke de Wert from Trondheim NTNU, who will talk about assessing the durability of new supplementary cementitious materials. Then I have planned for a short 5-minute break, and then we will continue with some recent research from Sweden, where Gilles from RISE will talk about the evaluation of new SCMs from a Swedish perspective. And Gilles will be followed by Liming Wang from Chalmers, who recently presented his PhD thesis. And he will talk about performance monitoring and quality control of concrete by non-destructive test systems. And then we will end the webinar with a short presentation that I will have. We will talk about implementation and use of SCMs in practice. And hopefully we will have some time in the end for some final discussions. So Ruben Snellings, as you've seen in the invitation, he works at the university at the KU Leuven in Belgium. And he has been involved quite a lot with work within RILEM, looking into supplementary cementitious materials. And he fairly recently also had a publication, which is a very thorough review of future and emerging supplementary cementitious material, which was also presented at the International Cement Chemistry Congress. Clarke de Wert is a professor at the Building Materials and Concrete Structures and NTNU in Trondheim. She looks also into the behavior and performance of cementitious materials, especially with focus on durability. So that will be an interesting introduction to this topic. And this webinar now is free for anyone to join. Normally it's free for members of the Swedish Concrete Association. And as a member, you will get access to this large network of people who are working with concrete. And you are also able to participate on study visits and seminars free of charge. And you can also work with committees where we develop guidelines, for instance. And you also have a member webpage with all member benefits. So any one of you who is not a member and would like to be that, I urge you to go to the webpage and apply for a membership. So that was the introduction, and I will now give the floor to, or the web to Ruben Snellings.
Thank you very much, Ingmar, for the nice introductions and also organizing this webinar. Has been introduced as well by Ingmar. Actually, this presentation has also been presented at the ICCC, or at least a selection of the slides has been presented at the ICCC in Bangkok 2 months ago, almost 2 months ago. And it's the reflection of a review that we made of the last 5 years of latest developments in future and emerging SCMs. So as you know, at every occasion of the ICCC, there's a collection of review papers that is being collected and published and presented as well at the conference. And this one was targeting new SCMs, basically. And I had the pleasure of working on this topic together with Professor Suraneni from University of Miami in USA, particularly covering aspects which are of importance in North America, but also beyond that in reactivity testing. And Professor Jürgen Skipstedt from the University of Aarhus, who was also great support in looking into the details of the chemistry of these new materials. So maybe to introduce, just stating a few probably well-known points is that we all know that partial substitution of Portland clinker by SCMs is one of the key solutions to reduce CO2 emissions from the cement and concrete industries. And we also probably have experienced, at least in Western Europe, that the availability of some of these well-known SCMs is becoming more limited and might be a limitation in further reducing CO2 impact of our materials. The market is playing, we have demand and supply issues, in some cases even raising prices of certain SCMs, such as blast furnace slag, above that of Portland cement. So there's a competition for good sources. That means that there's also an imperative or an incentive to try and explore new sources that contribute to performance, that are safe to use, to extend basically our clinker replacement and the use of SCMs in a new generation of low carbon cements. As a benefit, as an additional benefit, some of these new sources can be processed or reprocessed waste materials, as we've seen with fly ashes, as we've seen with blast furnace slags. They can be very valuable. And in doing so, we can introduce new materials into the SCM application market, but also provide solutions for these waste materials in a circular economy perspective. When going through the literature, we try to make a classification of what are materials used today, what are materials that are emerging, and by emerging we mean new materials that are fairly well tried and tested, but are still yet emerging on markets, in several markets, maybe not in Sweden yet, but for instance, perhaps in France or in the USA, they have been accepted by local standards. And in fact, it seems as transpiring from the literature that most concerns in terms of their use have been resolved. Not all. There might be some open question marks, perhaps in durability, or there might be some drawbacks, perhaps in workability and so on. But what is striking, if we look at the chemistry of those materials that we classify as emerging, is that they're fairly close still to the chemistries of the materials we fairly well known, blast furnace slag, fly ashes, and so on. For instance, calcined clays are fairly close in composition to fly ashes, while obviously recycled concrete fines, they're somewhere in between quartz and Portland cement, or silica and Portland cement. So they all plot in this sort of upper part. So I'm going to use the laser point. They'll all plot in this upper part of the ternary diagram. But that's not all. Obviously, there's many more materials being explored, and many of these materials are still in fairly early stages of R&D, and there's still quite a few remaining efforts to be done. And if we plot them on these ternary diagrams, we can see that they often have slightly distinct chemistries. For instance, plotting more towards iron-rich or alumina and iron-rich systems. An important point to make is as well that many of these materials require processing. We call that beneficiation processing. So we, from a waste material or from a low value material, we process it and we make it a suitable SCM. And in particular, this area seems to be an area of intensive research. Many researchers are looking into ways to upgrade or upcycle, let's say, ashes or slags of some sorts, or even recycled concrete fines. And it's actually in the combination of the processing and then the properties of the end product that most innovation is happening today. In general, if you look into what processes are being used, they could be classified as a function of their processing intensity. We can have fairly low intensive processing, such as drying and classification methods, which are used today. Comminution, also fairly common to the industry. Of course, when we have natural pozzolans or slags, we might need to mill them to some extent. But there's more intensive processing also being explored. Wet processing, washing, leaching in some cases, has been seen as quite effective in improving properties or resolving issues with some SCMs. Carbonation, obviously, is mineral carbonation is something which is really in the spotlight today for recycled concrete fines, for instance, where the CSH or the calcium non-carbonate calcium is carbonated and produces both the material which is reactive and can store CO2. Moving up the ladder, we go into even more intensive, energy-intensive processing. There's calcination treatments and even vitrification. Calcination of clays, obviously, but also vitrification of certain waste streams can give you a slag with interesting properties. So this is kind of a subdivision of the processes that we see being developed today. Before we dive into some of the, I would say, materials themselves, I think it's also good to highlight a few of the advances in understanding and evaluating SCM reactivity. With today's advancements in methods, for instance, in molecular modeling and so on, we've come to a deeper understanding. Of course, we already knew that reactivity in SCMs in many cases is linked to amorphous phases being present or the composition of a certain glass phase, which then eventually is linked to something like the silicate framework structure, whether it's more depolymerized, whether it's less depolymerized, whether there's more calcium in there, whether there's more silica in there, and so on. This is fairly well established, and it's also embodied in or incorporated in many of the standards. However, it does more than that, and I think recent research has, for instance, shown that we can develop the structural descriptors of the glasses much more to make them more reactive. For instance, here, this average metal oxide bond dissociation energy was developed and showed a very good correlation to degree of reaction of a slag phase or a SCM phase in blended cements. Also, the effects of minor elements have been looked into more closely. The effect of titanium as a suppressor of reactivity has been researched in the literature as well. The effect of magnesium or the magnesium to calcium balance as well was highlighted or was investigated by the group of Professor Skipstead, showing that magnesium mainly has this role as a framework depolymerizer, and that any other effects are rather subordinate to that. So there's continuous advancements on really trying to understand the basics of the chemistry of reactivity of glasses and SCMs. But that's good to know. But obviously, in practice, we also want to have ways to evaluate them more directly in terms of performance or reactivity. And there's been, in the last few years, quite some developments in reactivity testing. Reactivity testing of an SCM is obviously only a first step in a series of performance-based tests. So as you can see here, an SCM is a first step, but screening that is already very interesting to optimize processes, but also to eliminate off-spec materials or to focus on materials that are most of interest for cement and concrete producers later on. Obviously, there's other key characteristics, durability, environmental compatibility, that need to be tested other than reactivity. But reactivity is often seen as closely linked to performance and durability, so a good indicator, at least, of what an SCM could do in a cement or in a blended cement. So about these new test methods, there is a test method being forwarded by a RILEM committee and also adopted by ASTM now, which is called the R3 test. It's an SCM reactivity screening test in which the SCM is tested in a medium which is closely resembling the pore solution of a Portland cement. It contains calcium hydroxide, an alkaline solution, potassium solution, and some water. And it's mixed together, and you have a fairly fluid paste. And this paste, actually, the only reaction which is occurring is the reaction between the SCM and the Portlandite, so really only measuring intrinsic reactivity of the SCM. No interactions with the Portland cement. And in that way, you can measure from the heat release by isothermal calorimetry what is the reactivity. There's an equivalent method measuring bound water in the same paste by a rather simple oven heating method, so where you don't need a complex isothermal calorimeter. The test method scales or the results scale pretty well with strength development. For instance, here you can see the heat response of the test method compared to the relative compressive strength in mortar bars at room temperature. So this is kind of fairly good correlation between different test results, heat release results, and compressive strength. And there's been an establishment of where typical materials would plot in terms of reactivity, pozzolans, fly ashes, slags, and so on. The R3 test can be extended. There's some research on that aspect as well to measure calcium hydroxide consumption in the same mixes. This is a bit more challenging to measure accurately because we are in a mix where we have quite some calcium hydroxide from the beginning. So consumption measurements by, for instance, thermal analysis, are a bit more challenging. But there's also good good correlation to the heat release or the bound water there. But this depends a bit on the SCM composition. Obviously, if you have a slag which is calcium rich, it may consume less calcium hydroxide for a given degree of reaction than a fly ash, which is mostly siliceous. Calcium hydroxide consumption can be interesting for some durability aspects, which are particularly linked to calcium hydroxide presence, such as calcium oxychloride consumption, where good correlations have been seen, and ASR expansion. Obviously, reactivity and durability are reactivity can give indications on durability, but it's not as easy linked as to compressive strength or other performance parameters. Durability depends on many different parameters and is in general more complex to understand. However, screening a filler material from a reactive material is still very valuable because we know that cements containing reactive SCMs are usually more durable than cements containing fillers. Another interesting testing method for reactivity or giving an indication on reactivity, which is perhaps more closely linked to durability, is bulk resistivity testing on mortar bars or pastes. And also there you can see correlations with, for instance, this calcium oxychloride formation, and this is also interesting. It's very sensitive to differentiate these reactive versus inert materials, but the linear correlations that we've seen for heat release do not appear for the bulk resistivity tests. And there's still significant work ongoing in RILE MTCs to optimize the method. Going back to the R3 reactivity test, the summary perhaps shows that for these groups of materials that we introduced before, present, emerging, future SCMs, that here we scale from inert fillers to silica fume as a very reactive material. But it's also interesting to see where these new materials plot like. So biomass, ashes, or concrete recycling fines are typically on the edge of being reactive or not, while calcined clays have very high reactivity depending on their kaolinite content. High-grade kaolinites are very reactive materials. That's clearly shown in these test methods. What's also shown here is that if you do some beneficiation, and we'll talk about this a bit later, for instance, for non-ferrous metallurgy slags, you can transform an initially inert material in something which is having reactivity and contributes also to performance. Saying that, I think it's important to stress that it's not only reactivity which should be kept in mind for new SCMs, it's also environmental compatibility, health, environment, safety issues. These are imposed by legislation, so obviously we have to protect humans and the environment from potentially hazardous materials. Methods are usually available and harmonized. Limit values typically are nationally imposed, and I would not know how it works exactly in Sweden, but in Flanders it's working, in Belgium it's working a certain way, in the Netherlands slightly different, and so on. The typical parameters you might want to look at are heavy metal contents, and in particular whether these heavy metals are mobile. Emissions can happen during the first life when the concrete is in place, or during the second life when it's crushed and used again as, for instance, a road-based material. Radioactivity is another one. Some of these SCMs, for instance, these non-ferrous metallurgy slags, but also phosphogypsum, may contain traces of radioactive elements, so should be tested also and in terms of gamma ray radioactivity. And finally, and it's also quite important to follow up on this one is respirable crystalline silica contents, where crystalline silica should be less than 10 weight% in the below 10 microfraction. That's of course not saying that asbestos is obviously not not allowed in construction materials. However, we're just saying that in particular in the north, my experience is that some projects show that tailings can contain asbestos, so it's better to be avoided. Obviously, some legacy C&D waste might contain asbestos as well. Now, looking a bit more further in depth into the future and emerging SCMs, well, I selected a few of these which might be more relevant for the audience: calcined clays, recycled concrete fines, biomass ashes, steel slags, and non-ferrous metallurgy ashes, slags that might also have some supplies in Sweden. And that's not enough time basically to go over all of these materials. Calcined clays, I trust, and if not me, or somebody else probably will introduce these. Calcined clays are one of the main most promising SCMs in terms of reactivity, performance, and availability. And we see that these ternary mixes of limestone and calcined clay cements are really reaching the markets today. Perhaps not in Sweden, but in Denmark, in Belgium, in France, in many places in Western Europe, we start seeing the first calcined clay or limestone calcined clay cements reaching the market. So this is to some extent already known. What we see beyond these LC3 cements is that recent studies show that you could also try to use mechanochemical activation, so intense milling as an alternative to thermal treatment, in particular for those clays that are a bit less reactive, so the smectitic or the illitic clays, not the kaolinitic clays. And that co-calcination of these so-called illitic or smectitic clays with some fluxes or materials containing fluxes such as calcium or sodium or potassium can increase the reactivity by enhanced formation of reactive amorphous phases. Another interesting one, the pictures you see here are more of rice husk ash, but I believe that biomass ashes are also in Sweden on a potentially interesting supply. There might be some legislative issues. However, a recent study showed that on a global level, there's really large potential if one would be able to actually source and bring together all of these end products or waste products from biomass. You could have up to a billion tons of materials available every year. However, that really makes abstraction of many other useful uses of these materials, such as soil amendments, and the fact that logistics can be really complex and costly. So it's still to be seen in what constellations biomass ashes can really serve as a good supply of SCMs. There might be local situations where this is actually useful, but in many places this doesn't make much sense. On a material level, what's known is that from recent studies that, and it's actually confirmation across a wide range of biomass ashes, is that depending on the biomass source, whether it's herbaceous or woody or animal, you really have very different ash compositions. So you really have to be careful about what materials you're taking in and what the sources of biomass is. Those materials that produce siliceous ashes are best suitable and they are most reactive. So we're thinking here about herbaceous materials. Rice husk ash are a very well-known example of this. While on the other hand, calcium-rich and alkali-rich materials or ashes may compromise performance, durability. Compatibility is also sometimes an issue. They're not very reactive and may disturb the reactions of the cement, so one needs to be careful. And wood ashes, for instance, are typically calcium, sometimes even also potassium-rich. However, people have tried to resolve some of these issues. One important point is that firing should be controlled and probably optimized to obtain an ash composition or an ash crystallinity, which is optimal for reactivity. So firing and milling, so processing, is very important to improve water demand. Water demand is typically quite high of these materials. If there are issues with soluble alkali, washing or a leaching treatment can help. as well as trying to co-combust, and this is done sometimes already by standard in energy plants, is to reduce slagging of the ashes during combustion, is to add aluminosilicate additives. This can be ashes, other ashes, or these can be clays, for instance, and also that produces a reactive material. Another important one are recycled concrete fines. Obviously, they're available in most developed countries and will become more available in the next decades as many structures will reach end of service life and will need to be refurbished, replaced, or recycled. An important fraction of concrete recycling are the fines, typically between 30 to 40 to 50% of the recycling output. And in many cases, this is when it's used, it's considered as inert. However, lately, researchers, for instance, from Heidelberg Cement, have intensively worked on carbonation of RCF, where using a wet process or a moist process, they were able to make calcium hydroxide, CSH, or calcium aluminate hydrates in the RCF react with CO2 to form calcium carbonate and silica or alumina gels, which can be highly reactive. And it's interesting to note that these materials are indeed inducing quite significant gain in strength. You can see, for instance, here in blue, that these are the strength developments for the blended cements with carbonated recycled concrete fines. You can see a major increase by 7 days of the strength up to the level of the reference Portland cement. So it's an interesting material to work with if you can get it really carbonated. However, there's still quite a lot of research to be done to optimize this. First of all, the recycling technology, trying to recover as much of the hardened cement paste from the fines, so to separate it from the sand, basically, is really needed. The more sand you have, the more filler, the more abrasion on any milling installation, and so on. So getting rid of the sand is very important. Also in the processing, the carbonation processing, and in particular the upscaling of that process, needs to be done. But this is ongoing, and in the next few years we will know much more about this. Effects on fresh concrete properties. The materials tend to have an effect on increasing water demand. So that's of interest to further investigate, but obviously there are solutions to this. Durability is also being investigated, but we don't know too much about this at the moment, but we will surely have this in the next few years. Moving on, we go from concrete, we go to a major waste stream, steelmaking slags, obviously also of interest to Sweden and Swedish industries. Globally, most steel slags are generated in China, and well, overall we have about 200 million tons generated each year. But we have to say that probably this will become a little bit more, because we will see in the future that, for instance, direct reduced iron production processes for making steel or recycling, shifting away from blast furnaces to electric arc furnaces, will generate more steel slags. The regular steel slag you will find is largely crystalline and has little reactivity, may have free lime, which is not of interest, and may disturb your hydration process or cause expansion. Some may have heavy metals and that are leaching out. So all of these should be resolved. Recent advances have mainly been focused on trying to reprocess these slags. So mechanical activation seems to work to some extent to increase reactivity. Carbonation may work as well to increase CO2 uptake in the material, but also generate its reactive silica, as we've seen for the recycled concrete fines. And another one, interesting one, is to do high temperature slag engineering, trying to modify the composition of the slag so that it becomes more suitable for application as in SCM, for instance, by reducing its iron content to make a composition which is more similar to blast furnace slag, to quench it instead of slowly cool it to get a more reactive slag. And this is also what you can see in these results here, where you can see clearly For instance, that vitrified steel slags can have really nice strength developments, even compared to SEM1 in a 25% replacement. In combination with 5% of limestone, actually, one would be able to get higher strengths than the reference Portland cement. Maybe to wrap up, a final one on the go. So a non-ferrous metallurgy slag, something we have been working a lot on in Leuven as well. So this is probably a more local secondary resource. We have a lot of it in Belgium. I suppose you also have some in Sweden. And the majority of this is generated in copper production. And it consists mainly of iron silicates. And in the regular form, it's crystalline, hard material, for instance, used for abrasive properties. And as given, they are very lowly reactive or inert, and might even have some slight retarding effects. Recent advances go a bit along the line of what we've seen for steel slags, so trying to modify the composition of the slag at a high temperature by adding in calcium and aluminum will have a massive effect on the reactivity. So you will actually create a more reactive material. And also, if you then quench the slag, so making it amorphous, then you will retain reactivity and strength contribution. Typically, these strength contribution would be comparable to siliceous fly ashes. But on the other hand, you resolve the issue that many of these slags actually don't have applications at the moment. It should be said, of course, that they have significant levels of heavy metal. So if you can also reduce heavy metal leaching, or you can recover heavy metals at the same time, this is beneficial. What is interesting to see is this chemistry is quite different. It's mainly iron and silica, and iron 2, divalent iron, seems to be mobile in the reactions and can be incorporated in new type of layered double hydroxide. That's a bit like an AFM structure, amongst others. What we still definitely need to have more information on is on the long-term durability impact. Some concluding remarks on what's happening in terms of standardization for new SCMs. You probably are aware that in Europe there's new standards out on low clinker cements, EN 197-5 and EN 197-6. So the 5 covering combinations of well-known SCMs, but with higher degrees of clinker substitution. And the EN 197-6 looking into or allowing or specifying the use of concrete recycling fines, so also opening up opportunities for a new SCM. There's several things under development on the concrete level. So there's European standards considering the inclusion of reclaimed coal fly ashes or reclaimed GGBFS in the respective standards. But also we're working on drafting specifications for natural and calcined pozzolans as concrete addition on the European level. Perhaps it's also interesting to look across the Atlantic. So there we have the move towards new specifications for ground glass, for instance, updates on conventional SCMs, the introduction of the reactivity test, the R3 test, and the development is a specification, a general specification or generic specification for SCMs for using concrete, for any SCM, regardless its origin. And that's actually also perhaps one of the ways forward for new SCMs, not only to adopt materials that have been accepted in cement standards, in concrete standards and beyond. That's an obvious first step to try and facilitate this, but also to provide better guidelines for what we need to comply to if we develop new SCMs, how to introduce new SCMs. And finally, and that's a more audacious step, is to try and foster the development of a performance-based standard also on the cement level that will try to overcome some of the drawbacks of the current composition prescriptive system, where we really have this plethora of different SCM cement types that we have to specify again and again, and might become quite complex and confusing in the long run. So my conclusions is that there's a transition to new SCMs that is gaining momentum. We see global emergence of previously only locally used SCMs, off-spec materials being used, novel combinations being introduced, and also some new SCMs such as glass pozzolans or are concrete recycling fines starting to emerge. For other SCMs, we see that there are some challenges that need to be resolved, typically low performance, incompatibility, environmental incompatibility. And this implies if we want to use such materials that have these challenges, that we will need to be able to adopt intensive processing beyond what the milling that we do today, and that cement producers may need to move a step further into also processing their SCMs rather than just adopting them or in their processes. Okay, thank you for your attention very much.
Thank you, Ruben, for a very nice presentation. And as we can see, there's been quite a lot of development and looking into, since we're a bit short of time, I'll ask one question, and the audience they can send questions to me, and then we will see if we can answer them. But looking into the cement industry's roadmaps that has been developed, looking at what they think about alternative binders, they seem to look that this has quite a small potential. They're talking about 5 to 10%. What do you think about the future? Will we see more blended materials?
Yeah, in my view, their position is quite conservative on this respect, and I think that there's much more possible, maybe even double or triple of that, by moving towards really low clinker blends. And I think in the development of the roadmaps, the SCM part has been mainly considering these current well-known SCMs and their supplies. And of course, there you're more limited because you won't find much more GGBFS, you won't find much more coal fly ashes around. So I think this was the main limitation on that level. So I would expect that we could do more in terms of clinker replacement, actually. Yeah.
That's really good news, I think. Okay, thank you, Ruben, for a very nice presentation, as I said, and then we give the word to Klaartje.
Then so hello everyone, I'm Klaartje de Weert, and I'm a professor at the Norwegian University of Science and Technology in Trondheim, Norway. And today I'll talk about assessing durability of new SCMs by thermodynamic modeling. So I'm a civil engineer of education, and I graduated in KU Leuven in 2006. And in 2007, I started a PhD at SINTEF, so I moved to Norway within the COIN project. And during my PhD, I was lucky, and I was able to go on a research stay to EMPA in Dubendorf, Switzerland. And there I collaborated with Barbara Lotenbach, and I got introduced to GEMS. And ever since, I've been using GEMS to study cement hydration or durability related issues during my postdoc and also as a professor at NTNU. The picture you see on the right is a picture from the last GEMS course we held at EMPA in June this year. And you see a lot of new faces that are new to GEMS and quite some experienced people there. So if you, after this talk, would like to learn more about GEMS, I really recommend you to join one of these GEMS workshops or courses. They're normally held every other year. So stay tuned. So in this talk, I would like to, just a moment. Yes, I would like to first introduce to you what thermodynamic modeling of cement hydration is. Show you an example of using it for Portland cement, and then what happens when we include an SCM in the system. And then finally, I'll talk about how we use this thermodynamic modeling in the context of concrete durability. And to conclude, I'm a researcher. I'll point out some more need for more research in this field. So let's get started with thermodynamic modeling of cement hydration. So what is actually thermodynamic modeling in this context? So what we normally do is we try to gather input from your Portland cement, and you include some water because you're going to look at hydration. And what you need from your Portland cement is your clinker phases, your oxides, alkali oxides, magnesium oxide, your sulfates, and maybe also your calcium carbonate. If you're not that lucky and you don't have the full characterization of your cement, you could also simply use your oxide composition, which you can get from XRF, which most cement producers provide. Now, what we want to get out is the composition or hydrated assemblage when your cement has reacted. So you want to know how much CSH you have, Portlandite, your AFM and AFT phases. In addition, you get out your pore solution. So you know how much of it you have, and you also know the concentration of the ions in it, and thereby also your pH. So this is actually what thermodynamic modeling does. It calculates based on this input, the output, and it determines the phase assemblage at equilibrium by minimizing the gyps-free energy. And in order to do these calculations, we need thermodynamic data. We need thermodynamic data of the phases that conform and also of the aqueous phases. And the thermodynamic data allows us then to calculate which composition of these phases will give us the minimum gyps-free energy. This is a slide I borrowed from Barbara. And there you see that we use standard thermodynamic databases like the one from PSI for the aqueous phases, gaseous phases, and minerals. But then we also use a cement-specific database. And the most recent one is Data 18. And it gives us the thermodynamic data of your AFM phases, AFT, hydrogarnet, CSH. So the typical phases you would find in a hydrated cement. And all this data comes actually from solubility measurements at different temperatures and where you also analyze your solid phases. So a lot of work lies behind that data. And the very wonderful thing with this is that all this data is available for all of us. So the Data 18, the most recent cement-specific thermodynamic database, is published in Cement and Concrete Research. And if you look in this publication, you'll find tables with all the typical hydration phases you find in a hydrated cement. For example, here, AFT, hydrogarnet, AFM, and you'll find your gyps-free energy of formation, enthalpy, entropy, your temperature coefficient, and your molar volume. And not the least, you actually get to know who did the hard work to get you those numbers, so you get the references of the publications. Note that some of these lines are work for an entire PhD. But all that data is available to us, which is just wonderful. And then the only thing we need is a tool to do the calculation, to do the minimization. And we call this typically geochemical codes. Here I give some examples of freeware. I will be talking about CAMS most of the time because that's the software I use. But you could also use Freaksy. Gilles, who will be talking later today, I know he uses Freaksy. And you could also use SCMs. And SCMs is in a way a bit more user-friendly version of GAMS, or the interface is a little bit simpler. So if you after this talk would like to try SCMs or GAMS, know that there's tutorials available that can get you started with it. So check that out, check these links out. Perfect. So now we have all the tools to do thermodynamic modeling. So let's try to do this for a Portland cement. So we need the composition of our Portland cement to calculate the hydrated assemblage and the pore solution. So here I try to visualize it. This is the composition of 100 grams of a typical Norwegian Portland cement. So you have the calcium oxide content, silicon oxide, aluminium oxide, and other oxides. And I add 50 grams of water to this 100 grams of cement. And then I let GAMS calculate which phase assemblage I would get at equilibrium. And what you can see here, this is actually gram per 100 grams cement. You get quite a bit of CSH, some Portlandite, ettringite, monosulfate, hydrotelsite, and water. So you get the phases that will form at equilibrium. And you don't only get the solids, you also get the composition of your pore solution. So here you have it in molality. You see that the pore solution, the main ions in it are sodium and potassium, and it leads to a pH of about 13.7. The other elements are there, but they're in much lower concentrations. So if you want to see how much calcium or sulfur, I would have to use a log scale to show these concentrations, but they're also there. So this is what I could do for Portland cement. So what happens if we want to include an SCM, supplementary cementitious material? So if we want to include an SCM, we need to know the composition of our SCM. So we could add it also as an oxide composition and then see how it influences the output of our thermodynamic calculation. But here is a tricky part. What do we enter as the SCM composition? You could use the entire XRF, so the total XRF of your SCM, but as Ruben earlier said, quite a bit of it can be crystalline and inert. So if you're able to quantify the crystalline non-reactive phases, just as examples, quartz, mullite, hematite, you could check the oxide compositions of these and subtract it from the total oxide composition of your SCM, and thereby obtain more an idea of what the composition of the reactive part of your SCM is. And then include this into your thermodynamic modeling, because that's actually what's going to go into the system. But this can be a bit challenging. But when we've done that, and here I did it for, so on the left, we have the figure for pure Portland cement. And on the right, I have replaced 30% of the Portland cement with calcined clay. And you can see that that changes the oxide composition of your total cement. So you have less calcium oxide, more silicon oxide, aluminum oxide, and iron oxide. And again, I let it react with 50 grams of water. And what I get then is here on the left, it's still the phase assemblage I earlier showed for Portland cement. And here you see what happens when we replace 30% of our Portland cement with a calcined clay. I just picked a random calcined clay from one of our research projects. What you can see is that this calcined clay, when it reacts, it consumes all Portlandite in the pozzolanic reaction. And what it does, it forms more CSH, and it typically also forms or can form more AFM. And in this case, as we ran out of all Portlandite, we even formed stratlingite. So you can see that the pozzolan or the SCM is greatly affecting your phase assemblage. And it doesn't only affect the solids, it also affects your pore solution composition. So when we compare the pore solution compositions, we can see that the calcined clay considerably reduces the potassium and sodium in your pore solution, and thereby also the pH of your pore solution. So these are also things you can use SCMs for too, to calculate how that would change depending on your SCM. So this was a very fast crash course on how we use SCMs to look at hydration and how we can see how SCMs affect our hydrate assemblage. So how can we use this in the context of concrete durability? So what I'm going to do is I'm going to give 3 brief examples of how we've used thermodynamic modeling to look at durability. But there's much more. But because of the sake of time limitations here, let's look into these 3 examples. So we focus on first alkali silica reaction, or ASR, and a very brief repeat of what ASR is. So we need alkali originating from our cement, and they lead to the high pH of the pore solution, as we just saw. We need the presence of excess moisture, water, and a reactive rock containing reactive silica. And reactive rock will react with in the high pH environment and with the additional water to form reaction products such as alkali silica gel. And ASR leads to expansion and cracking of the concrete. It's a slow reaction, but we have quite some trouble with it here in Norway. But where do SCMs come into play here? So the role of SCMs when it comes to ASR is they can reduce the alkali concentration in the pore solution and thereby mitigate these deleterious expansions. So the SCMs will reduce the amount of available alkali for the reaction. And this is something Barbara and I wanted to look into in connection to a publication we wrote for the upcoming ICAR conference. We wanted to determine the minimum replacement level of SCMs required to prevent ASR. Or in other words, we want to know which replacement level lowers the alkali level in the pore solution below a specific limit. And here we assumed 300 millimole per liter. We did some literature search, and this is a lower limit that counts for many aggregates, but know that this limit is dependent on how reactive the aggregate you're looking at is. But we took, for simplicity, 300 millimole per liter. And then we used SCMs to see how does the replacement level of various SCMs affect the alkali concentration in the pore solution. Here I just took a few examples, but in the paper there are more. We did this for here fly ash and metakaolin. And what we do is we look at the volume of the hydrates formed per 100 gram composite cement, and we vary the replacement level of the Portland cement with fly ash. So going from 0 to 60 with fly ash and 0 to 60 with the metakaolin. And when we look at the hydration phases, you can see that the pozzolanic reaction of fly ash and metakaolin leads to the consumption of your Portlandite, as we've seen earlier with the calcined clay. And then you get more CSH and more AFM. You can see this even clearer for the metakaolin. And also note that we put a limit to the reaction degree of the fly ash and the metakaolin, and that's actually based on one of the figures Ruben showed in his talk. So here we have the phase assemblages and how it changes with the replacement level. But what we're actually after is how does that affect the alkali distribution? We know that sodium and potassium, they will distribute between the pore solution, CSH, and the unreacted Portland cement and SCM. And here I show the example for fly ash, and I split up the effect for sodium and potassium. And when we look at, for example, potassium, we see that a large part of the potassium is in the unreacted fly ash, part is in the CSH, and part can be found in the pore solution. And when we then plot the potassium and sodium concentration in the pore solution as a function of the replacement level, and that's what I did here. I did it for fly ash and metakaolin. You see also some points here. This is experimental data we found in literature. So the green line is for the sodium concentration, the blue for potassium, and the red line for sodium and potassium concentration in the pore solution as a function of your replacement level. And we said, or we assumed a limit of 300 millimole per liter, so it's slightly thicker black line here. And what we can see that for fly ash, that the total alkali concentration in the pore solution drops below this 300 millimole per liter at a replacement level of approximately 40%. Whereas for metakaolin, this actually already happens at a replacement level of 20%. So this gives an indication of how much of an SCM we need to include in our system to try to mitigate ASR. And there GAMS can be a very neat tool. So this was an example for how we use thermodynamic modeling to predict potentials of ASR and the impact of SCMs. Now let's look at an example for carbonation. And what we did here, this is a study I did together with Gilles Pluskilek, Anders Belderivert, Mette Geiker, and Barbara Lotenbach. And we looked at the effect of carbonation on the pore solution of mortars. And we combined thermodynamic modeling with experimental results. And we looked at a pure Portland cement and a Portland cement with 30% fly ash. And what we did here is we simulated carbonation by exposing the hydrated paste or mortar to increasing levels of CO2. So we start with 0 grams CO2 and we increase the level of CO2 our cement paste is or mortar is being exposed to. And we calculate the equilibrium phase composition upon exposure to this CO2. And what we can see for example, if you focus on the Portland cement, is the first thing that happens upon carbonation is your Portlandite is predicted to decompose and form more calcite, so the darker green phase. And in order to have all Portlandite reacted with CO2, we need a certain level of CO2. When we look at the fly ash cement, the pozzolanic reaction of the fly ash has consumed quite a bit of this Portlandite, so we need much lower levels of CO2 to consume all of this Portlandite. And another thing we can see based on this phase assemblage is that when Portlandite reacts to calcite, we get a nice volume increase. The calcite has a larger volume than the original Portlandite. And this has a clear effect for the Portland cement, whereas for the fly ash cement, there's only a slight increase. And this indicates that with Portland cement, we can have a pore tightening effect of carbonation, and that effect is not that clear for a composite cement. But we were interested in the pore solution. So here you see the graphs on the bottom show the pore solution, which is as a function of the CO2 added to the system, and which is in equilibrium with the solid compositions above. And we really wanted to know how do these SCMs affect the pore solution in the carbonated state. And that's important because that's where, when the concrete has, or the mortar has carbonated, that's where corrosion is going to take place. So what is actually the environment of the rebar in this carbonated mortar or concrete? But in order to know, because we combine this with experiments, in order to know which phase assemblage we approximately had in our fully carbonated mortar, we matched the carbonation state in our experimentally or our exposed samples to the calcium carbonate level, which was modeled. And the model calcium carbonate level is the green line. And we had measured in our fully carbonated mortar this level of about 20% of calcium carbonate. So our fully carbonated mortars, they were equivalent to the phase assemblage at about 34 grams CO2. And we did the same for our fly ash cement. We had less calcium carbonate there, and there we had an equivalent CO2 level of about 27. So in this, in these graphs, we're approximately here in this phase assemblage. And then we extracted the pore solution composition at this phase assemblage. And we compared it with some experimental results. And this is where Gilles used his cold water extraction technique to try to obtain pore solution composition in these carbonated mortars. And we have compared the experimental results with the modeled ones. And what we could see, first conclusion is quite obvious. When we compare the references here, non-carbonated with the carbonated ones, and the blue bars are for sodium and the green for potassium, we can see a decrease in the sodium and potassium in both investigated cements. And a decrease in available sodium and potassium means that we have a decrease in OH minus and therefore a decrease in pH and a depassivation of our steel. But that we knew. But what was nice too, we could actually see where the alkali went. They go to these silica gels, which actually absorb the alkali. Then a more striking thing was that we observed that upon carbonation, we got an increase in sulfur and chlorine in our pore solution. And that was both measured and predicted. And having an increase in sulfur and chlorine in your pore solution will actually aggravate your corrosion. And that's a parameter which is it's important to be aware about. Though in this case, we didn't see a very clear difference between the two binders investigated, but this might be very relevant for new SCMs, which potentially have more sulfur or chloride available and might affect actually corrosion rates in carbonated concrete. So this was an example on carbonation and how we use thermodynamic modeling to get a better understanding of the mechanisms. And finally, actually one of my favorite topics, chloride ingress. I'll just briefly touch into this, or actually it's more chloride binding. And here I'm showing some results from the postdoc of Arizu Baba Ahmadi, who's now professor at Chalmers. And during her postdoc, I worked together with her and a team of researchers. And what we looked at was chloride binding in different systems. So she had a reference Portland cement, a cement where she had replaced the Portland cement with 50% metakaolin. She used 50% also silica fume and a combination of metakaolin and silica fume. And what we see in this figure is the volume of hydrates per 100 gram composite cement for these 4 systems. And what we can see for the Portland cement, as we've seen earlier, we have CSH, Portlandite, ettringite, and some monocarbonate. And when we replace 15% of the Portland cement with 50% metakaolin, we have a reduction in the Portlandite content, so the pozzolanic reaction. We have some more CSH, and we get more AFM, as we've seen earlier. If we use 15% silica fume, we also have a reduction in the green Portlandite content. We get more CSH, but we don't get an increase in our AFM phase, as we're not adding more aluminates to the system. And if we combine 15% metakaolin with 15% silica fume, we actually consumed all Portlandite, so there was no Portlandite left, and we form a lot more CSH and some more AFM. So we had these hydrate assemblages to start with. And then I used GEMS, or Arizu used GEMS, to calculate what happens if we expose these systems to sodium chloride. And we used a high concentration, 2 mol per liter. And we looked at what happens with the hydrate assemblage. And when you compare the figures here on the left with the ones on the right, the main difference is actually that the blue boxes turn red. And the red is Friedel salt. So it's actually in the same family of monocarbonate, but instead of containing carbonates, it contains chloride. So GEMS predicts that most of the AFM goes to Friedel salt. So how do then these SCMs affect the chloride binding? When we have aluminate-rich SCMs, such as metakaolin, we'll form more of this AFM, and more of this AFM results in more Friedel salt and thereby more chemical binding. But the problem is GEMS doesn't tell us anything about the physically adsorbed chlorides because that's not included in the current CSH model. So we can't say how these changes in the CSH affect the physical sorbed chloride. So when Arizu in her study wanted to link these phase assemblages to the binding isotherms, so where she actually measures the amount of chloride bind per gram dry cement when varying the chloride concentration, she couldn't match these binding levels with the phase assemblages predicted by GEMS. And the reason why there is no direct link between the GEMS model and the binding isotherms is that we observed that the chloride concentration or the chloride content in the AFM actually varies, and it's not necessarily the value you get from GEMS. And you're not accounting for the role of CSH in the physical adsorbed chlorides. So here you can see that we need some more research on some of the thermodynamic data to actually be able to do this. So those were the 3 examples of how to use thermodynamic modeling in the context of durability, but you could do similar approaches for sulfate attack or leaching, and there are several publications on this, so if you're interested in that, just reach out. But so as I mentioned in the start, I'm a researcher, so I need to close off with where do we need more research? I don't want to get unemployed. First, a little bit on the limitations of GEMS, because GEMS is a wonderful tool, or thermodynamic modeling is a wonderful tool, but be aware that you need correct input. So you need to actually have a good characterization of your SCM to know what the reactive composition or the composition of the reactive part is. And you also need to actually give GEMS the degree of reaction of your SCM, because GEMS does not account for kinetics. And know also that if you don't have thermodynamic data of a hydration product or a reaction product of a deterioration mechanism, GEMS will not be able to predict it. It only predicts the phases you have given it thermodynamic data of. So that's why I really want to stress that always try to combine GEMS with experimental verification, so you know that you have actually, you can identify the reaction products you predict. And similar with the pore solution composition, it's a very nice verification of your model. I mentioned when talking about carbonation that the thermodynamic modeling can show or indicate a pore tightening effect. But there it's important to be aware that thermodynamic modeling only predicts the total pore volume. It doesn't give you any information on pore connectivity. So if you want to do transport modeling, you should combine your thermodynamic modeling with a transport model and with a characterization of your pore connectivity, because GEMS can't do that. And then finally, the further research. What I tried to show with the chloride binding example is we need more thermodynamic data on CSH. In all the examples I've shown, you see that CSH is the main hydrate. So, and currently the model doesn't account for aluminum uptake, sulfur uptake, and chloride uptake in CSH. And as it's the main hydrate, small variations in uptakes of these elements will actually affect a lot your hydrate assemblage you predict. So I want more work on that, and I'm in for it. So that brings me to the end of the talk. I need to, when talking about thermodynamic modeling, I have to say a big thank you to Barbara Lotenbach, who introduced me to GEMS, and who's a wonderful person to work together with. She has a part-time position at NTNU, and I'm very happy about that. And I also want to thank former supervisors who supported me collaborating with Barbara, and not the least colleagues and PhDs and postdocs and master students that have helped me to do this work or have done most of the work. And then also not the least the projects which have made it possible to do this research. So that was, here you see Barbara in the middle of this picture. She, besides GEMS thing, she also likes to walk in the mountains. So that was it from me. Are there any questions? Or I'm going over time.
Thank you, Claudia. You're a bit behind the schedule, but I was
sorry.
No. I was expecting that. I was too ambitious in the schedule. So we have 2 minutes for questions to Claudia, if anyone has any. If not, then I'll start at least and say thank you for the nice presentation and that you show how useful this type of tools are. Mm-hmm. And given what Ruben presented before, do you think that we can use this type of modeling combined with experiments for really accelerating the implementation of new binders which we haven't used before?
Yes, I think it's a very nice tool to combine with experimental results. But what is and it's actually being done. But Ruben told about several SCMs that are a little bit more out of this range where, like, maybe higher aluminum contents and out of the range what we're used to. And there it's always a challenge to make sure that we have the thermodynamic data of the phases that will form in those systems. So it will open up the door for more research on actually gathering thermodynamic data for potentially new hydrates. So I think that's the challenge and maybe the beauty of what we have ahead of us.
I'll give the word to Jill.
Hello, everyone, and I'm going to talk a bit more on the new SCM and how we deal with it in Sweden. And basically, I'm going to share a summary or an overview of the projects that we have in RISE. So not all this work is done by me, but actually a lot of colleagues also participated there. And I wanted to start to show a bit more of the Swedish market and the possibilities that we have. And historically, Sweden has been a country where we didn't use a lot of SCM, so the clicker content that we use are quite high, and it's only quite recently that this minimum clicker content that is allowed has been reduced significantly. So now for most environment, we can have a minimum clicker content of 35%, which lets us a big place to play with more materials. So as Ruben mentioned, there's all those common SCMs such as silical fume, blasphemous slag, or coal fly ash are really low in availability and the availability will decrease even more in the future. So we wanted to see what other possibility we have in Sweden if we look at the available local resources. And there are three materials that stand out a bit because of their actual availability. So the biomass ashes, the steel slags, and the clay. So the number here looks a bit scary, but it's actually because there's not a lot of clay that is actually digged, but a lot of it is actually available in the country. And I'm going to start with the clays. So a few years back, we made an inventory of what we have in the country, and we received samples from different parts, and we categorize them into according to their mineralogy. And we saw that we have mainly two types of clay in the country. So in pink dots, here is where we have the conitic clays, and the blue dots correspond to the ilitic clays. As is clear, we mostly have ilitic clays in Sweden, which was not what we hoped for, because the conitic clays, it's what is actually really easy to activate and actually use with cement. For ilitic clays, we cannot just calcine them and mix them with cement. That will not work that well. This is illustrated in this graph here, which was the XRD pattern of clay containing both illite and kaolinite. In yellow, it's the raw material, and in blue, it's the material after calcination at 600 degrees. And we see that for kaolinite, the peak actually disappeared. It shows that it's now amorphous and reactive. And then we participate with the hydration reaction of cement. But for illite, nothing really happens. And if we increase even more the temperature, we have the risk to form unreactive phase, so which will be even worse. So we still wanted to use our local resources in Sweden. So we wanted to see what we can do to activate this type of clay. So we'll show some result of R3 test only on ilitic clays. I won't talk more about this test because Ruben detailed it quite a bit in his presentation. And so here on the graph, I present the total heat at 7 days for different material. In gray, it's the ilitic clay without any treatment. And those different green bar is the reactivity of the clay after mechanochemical activation, or MCA, made in this case by ball milling. And we see that depending on which parameter we use, we have quite an impact on the reactivity. So it's important to take care of the actual parameters that you use for such activation. But also we can see that with the proper parameters, you can have a reactivity that it's actually quite good. For a normal calcination, as expected, the result is not that great. We also tried to combine those two methods, and there we have an even higher reactivity, which is actually pretty high for ilitic clay. We tried also flash calcination. So we are still paying on the parameters here, so it's not optimal, let's say. But the idea here was to give enough energy to the system to have this phase transformation, but without having the formation of unreactive phases that I mentioned before. So for example, for flash calcination, you go in really high temperature for really quickly, and you stay there for a few seconds, and then it's cooled down again very quickly. So we hope that we don't have the time to have those unreactive phase to form. And it looks like it's working. And here is for the comparison, I also put the result of the kaolitic calcine clays. So what we can see when we have all those data is that we can actually have quite good result with ilitic clays and even comparable to what we have with kaolitic clays. But now that comes also with the bad news, is that the mechanochemical activation is quite challenging to do in industrial scale because of all this energy that it requires, especially for such big amounts that we would need. So we still went a bit further with all our technique here and looked a bit more what happened in the cement paste level. So we took a SEM1 and replaced 30% of it with activated clays, the one that have the yellow star here. And we looked the iteration on the cement paste. Here's the result for the isothermal calorimetry, and it's the total heat after 7 days of iteration at 20 degrees. And we know that this value is directly linked to the strength of the product. In gray here is the value corresponding to the reference cement, so only cement, no clays. The pink will still be for the colonitic calcined clays, and all the other one for elytic clays with the different treatments, MCA plus calcination, and the flash calcination. So it's quite clear that in every case, we are actually very close to what we could reach to colonitic clays, even higher in certain cases. And in all of those methods, actually flash calcination is something that is doable at industrial scale. So it looks like a perfect match to activate this type of clay. Especially, as I said, we still can optimize those parameters and reach something even higher here. Now I'm going to give some indication of the type of performances that we can hope for this kind of, when using this some concrete with clays. This is I'm going to show you values for colonitic calcined clays, and with this specific binder, say mixed design, sorry. So for the binder, we have a replacement rate of about 50% with 30% of calcined colonitic clays and 50% limestone. And of course, the results are really depending on those parameters here, especially the water and the type and amount of admixture that you put there. But it still gives an idea of what we can reach. So first for the strength. So on the concrete cubes at 28 days, we can reach a strength of up to 84 megapascal, which is not bad at all, quite high even I have to say. And we looked at some durability resistance as well on the accelerated lab test. Here's the result for the chloride resistance. And we place ourselves in what is considered to be a very high resistance material. And for the carbonation here, we will be in a more normal resistance area. So with this kind of material, we can have high replacement of cement, and this is still linked to great performances. And now we will still have to do this work for elytic clays, so after, for example, flash calcination. And of course, this also linked to a really big decrease of CO2 emission of, let's say, about 40%. Yes, so that was for the clay. Now we can go for what we are doing or what we have done for the steel slags. As I was mentioning in the introduction, we have quite a bit of steel slag that is produced. But this high amount actually is not just one product, but represents a variety of products, depending on how they are made. So Ruben also presented all the different types of steel slag that we can have. Also the cooling will have a big importance. So depending on what type of slags we have, the use that we can make of it will, of course, be different. So an SCM, filler, aggregates, it's all depending on how they are made. Some issues also been indicated when we talk about SCM, which I'm focusing on today. It's a lower activity. For example, you can have the formation of gamma C2S, which is known to be not reactive. So if you have a lot of this phase, it's a bad sign, at least for use as SCM. Or the expansion problem if you have a lot of free lime or free magnesium oxide. I'm going to give some example now what we did with a sample coming from electric arc furnace and tunnel kiln. So from the same plant, but just different product line. Still in the cement paste level with 30% replacement. And to follow this, the heat that is released by isothermal calorimetry. And so the results are put here and presented with a 100% cement paste. So I mentioned earlier that this kind of value can be directly linked to the strength. But in this case, we have to be careful because if we have, for example, free lime, this kind of material, when mixed with water, will give a really high exothermic reaction. So that will impact a lot of your total heat that you measured at 7 days. and that in this case will not be directly transferred to strength. So we need to look actually a bit more on what is formed. So we did some TGA and XRG analysis over different time. Here I just saw the TGA result in terms of evolution of Portlandite content or hydrated water, which is directly linked to the amount of hydrated phase that you formed. So for the first steel slag for the tunnel kiln, what is mainly formed is actually Portlandite. So we also have some in the original raw material, but some is formed clearly over time. And we also detected some limited amount of extra formation of AFM phases compared to the reference. This was done by also TGA and XRD, but again, it's not shown here. For the other type of slag here, it's mostly the formation of additional AFM phases that we have seen, and mostly at late ages, because that we can see in the hydrate water content. Up to 28 days, the amount of hydrated water is significantly lower than for the reference. But at later ages, we actually completely catch up, which means that it's a bit of a lazy guy, but it looks like it works. So that was to really emphasize what I was saying before, that depending on what type of slag you have, you really have different hydration properties. So it's more a case-by-case scenario that you have to deal with. We made some strength development measurement on mortars. Unfortunately, we don't have the late value for the electric arc furnace steel slag. But for the tunnel kiln at 81 days, we had a decrease compared to the reference of about 20%, which is maybe not that great. But for the other one, we would expect a stronger strength increase because of this later reactivities that I was mentioning before. But although I think it's not extraordinarily good result, but this was by using the material raw without any treatment or pre-treatment whatsoever. So this could actually be improved quite a bit. So there is many possibility for that. In this specific case for the tunnel kiln, would be, for example, possibility would be to mix it with a polymer material because of all the Portlandite that was formed or also already present from the beginning. Also possible to do a grinding activation, this lead to a more homogeneous material, a finer material, which will be more reactive and therefore have improved hydration properties. It can also solve the expansion problem with, especially in the case of wet grinding, to get rid of the free calcium oxide. You can change the actual ways the slag is produced. So by direct collaboration with the producer, you can it's possible to influence the chemical composition and therefore again improve the hydration properties. If you fasten the cooling, you have a more amorphous content, which is also something that we want to have. Precarbonation would help again for the hydration because it can lead to the formation of aluminous leakage layer at the surface of the particle. That's something you would like to do, and it's very good also in the way for CCU and CCS. Precarbonation can also help for the expansion problem by turning this free lime to calcium carbonate. So those are the few examples that we are working on. Sadly, I cannot share data on those, but those are the leads that we are working on. Now for the last part I wanted to show, so the biomass ash. We have an ongoing project in which we are retrieving a lot of different ashes from a lot of different companies all over the country. We received either fly ash, bottom ash, or a mix of the two, mixed ash. All of those come from different type of producer, but energy producer, pulp and paper, or municipality. So we have a lot of different raw feed. Depending on what was used to make those ashes, we made a pre-screening. So everything that comes from recycled wood, we put aside because then there was a risk of paint containing heavy metal. that you don't want to have. But still, because of all this variety, we were a bit afraid of the variation in composition of all those ashes. So we made constant analysis of all the sample that we get. And here it's an example of the composition in terms of silicon, aluminum, and calcium oxide for different plants. So all those different E2, E1, E4, those represent different plants. And if one group has 7 bars, it's also, we made also the analysis at different time during a year of production. And also we differentiate the fly ash from the bottom ashes. What we could see is that the variation between the sample is mostly due to the plant of origin, that the variation in time in the same plant is actually not that big. So we were at least less important than we were expecting. Of course, we have all other components that we don't want to have, such alkalis, chloride, or sulfate. So you need to recondition the ashes. We did that with some washing, and we're studying the different parameters, such the liquid to solid ratio, the time of the leaching process, how many times you need to do it. And the result for some sample are here. So before in blue and after the reconditioning in red. So in some case, we could reach acceptable limit. So this white line are the limits that we have in the standard, so we cannot go higher. So in some case, we are still quite way above those. But it still seems that in most cases, we can get rid out of them and be in a good level. But then the idea to follow that, to compensate this kind of those two problems. So in terms of if we have too much of andesite component even after washing, or if we also have too much variation between the different plants, was actually to make blends of different sources to kind of flatten out all those differences. So we made some, not a quick test, but more F3 analysis on different blends. I will go quite quickly there. So it's different blends, either just fly ash or fly and bottom ashes of different type of industry. And we compare them to a commercial coal fly ash. And then the result was actually quite good, with some blends having relatively, similar reactivity than the coal fly ash, or even higher in some case. And it could also show that we could use the bottom ashes after grinding, of course, which was actually a bit nice news, because in the total production of the biomass ash, it's the bottom ashes that are made in the most. So it's good to know that we can actually use them as well. And now what we think in terms of strategy for the future, it's to make some kind of categorization of the ashes in terms of composition, of how easy it is to retreat them, how reactive they are, and to explore different scenarios in terms of making blends. Maybe make regional blends to also decrease the transport that will be needed, or one big national blends, or blends depending on different quality to make different products, but then one would have to think about what criteria do we want to have. Yep, so that was the brief overview of what we are doing at RISE. And so here is the name of my colleagues that work for the different type of materials that I mentioned there. So if you want to go into contact, don't hesitate. I also wanted to mention the project BEDCRIT, which is a national project that brings together all the entire value chain for the cement and concrete in the goal to have a common climate neutral strategy to reach to reach a climate neutral production. And this includes, of course, the use of SCM, and it also promoting the research on new type of SCMs. And finally, thanks for you for attending the webinar, of course, and to all of our industrial partners who co-finance a big part of the result I showed here. So thanks a lot. And maybe there's time for questions.
Yeah, thank you, Jill. We actually have a question in the chat about the mechanical activation of the clay, and the question was if it's stable over time or if it will deteriorate.
I'm not you mean if the material will get less reactive over time?
Yeah, less reactive over time.
This we haven't checked, but I would well, actually, we have checked indirectly because in some case I reanalyze the same sample to see the reactivity after maybe 6 months after I made it, just to check the repeatability of the measurement, and it shows exactly the same. So I guess it's a stable product. And
yeah. So that's good to hear.
Yeah.
Okay, then I hand over to Liming.
Thanks, Ingmar, and hello everyone. I'm Liming Huang. I'm now a postdoctoral researcher working at Chalmers University of Technology, and also thanks to Swedish Concrete Association for having me in this seminar. I'm going to share some of my results that was done during my PhD project. So it's about monitoring the performance of the concrete containing SCMs with a non-destructive test system, and has some potential for quality control when we are implementing different kinds of SCMs. So here is I have 5 aspects, and the last part is conclusion. I will first start with a really short introduction of this system, and it's mainly about in situ monitoring the electrical conductivity of the cement-based materials, as Ruben also said in the previous presentation. Bulk resistivity is a good promising parameter for assess the reactivity. So we have established this system based on this Webbinarium method to monitor the electrical conductivity of cement-based materials. We have 2 outer electrodes to give power, and then the inner 2 as a signal collecting, and to collect the voltage difference between 2 points inside the concrete specimen. We have this version upgraded from the lab to toward the on-site monitoring. And we also include the temperature sensor on one side or end of each layer to measuring the temperature, so that we can normalize the result at the on-site to a reference temperature for a better comparison. That's the brief introduction of the system. So I also want to say some words about why this conductivity works for monitoring performance, like strength and also durability index, because we can simplify a concrete system into 2 main components, like the insulative and the conductive. The insulative part is mainly the dry solid and also includes some air inside or empty pores. And the other part is conductive. And we can simplify it, classify it as liquid pore solution. Of course, we include some part of interlayer water from the CSH or some other layered structure hydration products. But to simplify, we classify them into liquid pore solution part. So during hydration or drying or the ingress of chloride, the volume of conductive component, also the concentration will change, so that we can follow them by the conductivity change. To validate this test system, we have cast 11 samples by using the same one with 3 different kinds of water-to-band ratio. And for the SCMs, we have this well-used type, like fly ash, slag, and limestone as filler in the P3 series. So if we have a look at the first, the early age hydration process, we can see that it can really replicate the hydration kinetic. As here we show in comparison with the isosomal calorimeter test, like we can reflect the silicate reaction peak and also the illuminator reaction peak. And for long term, we can also collect the data until maybe longer than 1 year. Here I just show 1 year because it's some data published in journal, but Now we keep the sample, and we have collected the 3 years data. It still works really good. I mean, the tendency really matches this curve. And also we see that after 1 year, the effect of fly ash can be clearly identified or like measured by the electrical conductivity change. So what we can extract from the electrical conductivity or resistivity data is like here I present some parameters, like try to quantify the correlation between the electrical properties of cement-based materials and the pore structure, like pore connectivity parameter, as Claudia has mentioned, that is important for the durability modeling or prediction. And we have formation factor, which is defined by using electrical conductivity of pore solution and to divide the electrical conductivity of paste or concrete, which part we can measure or monitor by device like the conductivity of paste. And here the second equation shows the correlation between the formation factor and the volume of pore solution and connectivity of this pore solution. For the conductivity of pore solution, we can estimate or assess by the concentration of ions in the solution, which can be basically predicted or calculated by using the composition of the binders and the amount of evaporable water. I will not go into the details because of the time limitation. So if you are interested about process, please go to read some details in our publications. So we have the predicted or calculated conductivity of pore solution, and we have the measured conductivity of paste. So we can calculate the formation factor evolution over time for different binders, different pastes. And on the figure in the left, we see that in the first few hours, the formation factor keeps almost constant, meaning that there's no, or there's very, very limited change of volume of pore solutions or connectivity of this thing, meaning that no significant structural change. To be better analyze the structural change like rate, so we define the average growth rate of formation factor as AF to use the formation factor divide the hydration time. We see on the right figure, the evolution of the AF is somehow in the same shape of isothermal calorimetric data. And then furtherly, we connected the inflection point of this AF to compare with the final setting time and the initial setting time measured by the standard methods. We see that the final setting time has a good linear relationship with the inflection point time of AF, which means that these measured electrical properties can reflect the setting process of concrete with different SCMs, which is also critical for implementation of SCMs. So after final setting, what we are caring about is the strength development as presented. In here, we try to extract the correlation between the formation factor, or actually it's between the porosity of the system and the compressive strength. So here I just show the final results, like deduce the correlation between the formation factor and the compressive strength. About the details, please go to check our publication. But in general, we try to describe or to validate this identified correlation between formation factor and the compressive strength. Firstly, we have a look at the figure B, that it describes the correlation between electrical conductivity and the compressive strength. In general, it describes good correlation, but if we transfer the electrical conductivity of paste into formation factor by use the conductivity of pore solution, we can get a better correlation between the formation factor and the compressive strength. And in two different descriptions of correlations, both in A and C, we can see describes very good. So which means that this parameter can indicate the strength development of concrete with different types of SCMs and even with different water to binder ratios in one equation. To furtherly apply or try to validate, we also had casted some on-site samples. Thanks to the good cooperation between Chalmers, Thomas Concrete Group, and NCC, we have casted a specimen on-site and exposed them on-site, and then use our system to monitor the conductivity evolution of on-site samples. After I got the data, I tried to use the empirical function we got from previous slides to predict the stress development of on-site sample. We can see it matches good with what has been measured in the lab, at least for 28 days and 56 days. This strength is really close to the predicted line. And interesting point is here, the on-site concrete has used different types of cement. For the research, we use cement one. Here we use the bigger cement, and also different slag replacement level, different water band ratio, but it's still like somehow fits good in this prediction. And talking about durability, I think there's some concerns about moisture problem induced by use of SCMs. And we see here by measuring the vapor diffusion, we know that blending of SCMs will decrease the vapor diffusion coefficient. Also, will change their moisture dependency of this diffusion coefficient. But if you try to use the formation factor or electrical properties to describe this effect, it matches good. I mean, at least for the RH condition higher than 75%. The correlation between inverse of formation factor and the vapor diffusion coefficient is really, I mean, more or less linear correlation at high arch intervals. So with this technique, we are also trying to monitor the drawing process. So I did not include the data here also still because we don't have enough time. So, but hopefully in the future we will publish like some of these results. It's also possible to review the moisture profile inside the concrete samples. So possible to resolve the concern of moisture problems while we are implementing the different kinds of SCMs. It's the same for the chloride migration coefficient. So here we can see a simplified prediction equation based on the formation factor we have monitored. We can predict the effect of SCMs and water-to-band ratios on the chloride migration coefficient under this RCM rapid chloride migration test mode. And not only for our results, but also I try to put some results from other publications in this predictor curve. It also fits really well in this line. Yeah, this system is working good in this previous section, but still have a lot of like open questions. We need to do more research. Like we try to, here we have identified one interesting question. We try to monitor the chloride ingress of concrete samples, use this Ponding method. But as we can see here on the A figure, the normalized electrical conductivity shows continuous decrease, which matches well with the modeling. But what's the real effect is the leaching of potassium and hydroxyl ions has a strong like spring effect of ingress of sodium chloride. So we cannot really extract the chloride ingress, but instead the leaching effect from the chloride from the electrical property profile. And also it will influenced by the saturation degree, blending of different SCMs, and also exposure concentration. So we still have many interesting points, need to do more work on application this in this field. So to wrap up, I will just say that this system will have a good promising potential to use to assess the reactivity of different kinds of SCM, and also maybe can be used for the mixed design and can monitor the on-site quality of concrete casting on-site, and also indicate the durability of concrete with different types of SCMs. But we still have many work need to do to make it apply good in monitoring the chloride ingress carbonation in the phase 4 and all the other applications. I would say thanks to to our hub groups at Building Materials Group, and also appreciate the collaboration with Thomas Concrete Group and NCC and all the other colleagues working together. Say thank you, and also we appreciate the financial support. I think that's all for my part. Thank you, and I don't think we have any time for question, but please feel free to send emails.
Thank you, Liming. I think Ruben in his presentation, he mentioned this conductivity measurements as a possible way, but then I didn't think he was considering the formation factor that you are using, which I think is an improvement, because then you can really understand what happens. And that also links well with what Klartje presented, where you can model the pore solution with the GEMS and thermodynamics modeling. So
yes, that's true. Yeah, we found some interesting indicators can connect both the strengths and even the transport process.
Yeah,
thank you.
So we'll continue with the work with this type of measurements, and hopefully we will be able to improve how we monitor new type of binders and also in the field as we tried here. Wrap up this webinar with some thoughts about implementation and use of new SCMs in practice. So of course, I mean, as we all know, that concrete as a material develops gradually. Preferably it should be also controllable, and it goes from a liquid plastic state to hardened concrete. And in between there, you also need to consider how you will finish if you have a floor like this, that you need to do a floor finishing, leveling the concrete, and then finally we will have a structure standing there. But in between, a lot of things can happen, of course, when we are talking about concrete. And generally, when we look into concrete, we can look at the time from mixing up to end of life and recycling. And in the beginning, of course, control of workability and workability retention is very important, because the concrete needs to be mixed, transported to site, and cast. Then we come into what Ruben was talking about a bit, and also Liming, that we know that during the first couple of hours, not much happens, but then we have start of the hydration, and we have this increase of heat development, which is connected to the early strength, and later on we can, in this period, also have problems with causing cracking, plastic shrinkage cracking in the fresh concrete. If we have material that becomes retarded, for instance, we can also have problems when we remove the form after a couple of days. And if we look a bit further on, we can have problems with thermal cracking or shrinkage cracking. And in the end, what Klartje was talking about, durability of the concrete. So all this time from mixing up to end of life, we need to consider when we are looking at new materials. And when we're looking at supplementary cementitious materials, we, of course, looking at how can we utilize these properties. A big drive, of course, is the environmental impact. So we want to use materials that can lower the impact of the carbon footprint of the concrete. But we can also use materials to improve the workability or the rheology of concrete, where we, for instance, can use materials like fly ash, which has a positive effect both on viscosity and yield stress. We can look at materials that gives lighter color or reduces the heat development, for instance. And also how they influence and affect durability. So when we start looking at new mixes, of course, the rheology and the effect of new binders on viscosity and yield strengths, and also thixotropy is extremely important. And we can use materials where we try to work with how it influences the yield stress and viscosity. As I mentioned there, fly ash and also silica fume is very good at reducing the plastic viscosity, which can be an important parameter. So knowing the materials, we can work on how to design the concrete and designing it for an appropriate use. Then when we are mixing and transporting the concrete, we need to know that we have good slump retention, which is generally affected by the compatibility between the plasticizers and the binders, how much is absorbed on the surface of the material and how reactive the material is. With some materials and some cements, for instance, we can get quite a big slump loss because ettringite is formed on the surfaces and we lose the effect of the superplasticizer over time. And then, as I said, during the setting time, if we have drying condition, evaporation, and shrinkage, we might have problems with plastic shrinkage cracking, which forms in the concrete when it's still plastic. It hasn't really gained any strength. And the drive here, of course, is the shrinkage development, but also how the pore pressure develops and contracts the concrete. And if it does this in a period when the concrete is very sensitive, you may have cracks which can be very wide and of course lead to durability problems. And here are examples from a PhD thesis that Oskar Esping did in 2007, where we looked into autogenous deformation, measuring the shrinkage of the fresh concrete 30 minutes from mixing, where we looked into different mixes and looking into, for instance, the effect of silica fume, where we could see that it increases the shrinkage, and that we can also work with shrinkage reducing admixtures, for instance, to reduce it. And of course, the drive for this is the hydration, but also how this early hydration drives the pore pressure development. So if we have a concrete that is exposed to drying and loses water, then the pore pressure will develop quicker. But also in the sealed specimen, we will see this pore pressure develop, and this causes the contraction of the material. And with new cementitious materials, we need to know how these influence this type of behavior. Then for the contractors, of course, they need to know that the concrete hardens quick enough so that they can do the floor finishing or strip the formwork. So here we need to look into the impacts of new SCMs on setting time and early strength, and if we can use traditional accelerators, or if we need new accelerators to improve the early strength development, especially when we have cold weather conditions, for instance. So when we are looking at implementing new materials, what is it that we need to think about? And here are some of my thoughts. Of course, the fresh concrete properties are important. Rheology and workability and the water demand. We don't like materials that have a very high surface area, which might lead to very sticky concrete with high viscosity. Such concrete will be difficult to pump and also more difficult to work with for the contractors. We need to know that the materials that we're using are compatible with admixtures. And of course, there is a lot of research ongoing at the admixture suppliers. And it's both plasticizer retarders, accelerators, and air entrainers that need to be compatible. And the impact of some new SCMs on workability, retention, and rate of setting needs to be known and controllable. So admixtures are important. And they should not be sensitive to large workability loss, or even worse, that we actually have an increase in workability of what we call fluidification during transport. And the time from when the concrete starts to set and you really reach the final setting time shouldn't be too quick, because then it might be difficult to do the floor finishing. We need to look into this early age plastic shrinkage cracking, how new SCMs affect bleeding, shrinkage, setting time, and how the pore pressure develops, and if new binders are more sensitive to this type of problems. We also need to look at early strength development, as this is important for formwork stripping, but also the risk of early freezing in the winter. And also the long-term properties of concrete, such as strength development over time, what happens after 7 days, 28, up to 90 days, and even further, how they affect E-modulus, shrinkage, creep, and fire resistance. So when we are looking at implementing these new materials, we need to consider the whole change from the mix design, the mixing, transportation, and up to long-term behavior and durability. And that was the final slide. And I'll stop sharing and see if we have any questions from the audience. If we don't have any questions, I hope this seminar has been, or webinar has been interesting for you. And if you have any questions afterwards, you can always email me or some of the presenters so that you can get more information if you would like to. So thank you all for this. Bye, take care, and have a nice Christmas when it comes.